And hi everyone, my name is Khronos, and I'm from University of Bristol. I'm a PhD student there at the High Performance Computing Group. And today I will present our work titled Optimization and Evaluation of Brief First Search with onAPI cycle on Intel FPGAs, from describing algorithms to describing architectures. So before diving too deep with the technical details, I want to share an interesting fact with you. So we all have a mutual connection with Pep Guardiola, a famous football manager. And for my case, no, I'm not a professional footballer. And yes, we are both, but that's not the only connection that we have. So according to the 6 degrees of separation phenomenon, we are all like 6 or fewer connections away from each other. And the key part is, how can we find these middlemen in the middle so that we can figure out the connection? And since we all know the connection graphs are not like 2D, it's all 3D and it's very complex. And here we employ the brief first search algorithm to find these connections and how can we find the details about it. So our agenda today is I will introduce you briefly I will introduce you FPGAs and brief first search algorithm. And later on I will introduce you to our two approaches for the solution, memory BFS and streaming BFS. And later on, I will talk about our performance evaluations. And last but not least, I will finish with a summary and quick conclusion. So a brief introduction to BFS, like the FPGAs are going to be like, so what we mean with FPGA is the field programmable gate arrays. And there are two major players in FPGA domain, AMD, which was previously Xilinx, and Altera, which was previously Intel, and then they started first Altera, then switched to it, like Intel bought it, and then now it's going to be a separate company, Intel, from Intel, and it will be called Altera again. And we used to code with hardware description languages, such as VHDL and Verilog. And in general, FPGAs offer massive parallelism, which allows us for each application to have operations customized, and we can specify one location for the data to flow from the FPGAs. And the other thing is we have flexibility of reprogramming. So let's say you have you need to add new compute units, or you need to add new functions to your design, so you can remodify your architecture. So our aim is to explore the Intel onAPI cycle to achieve better performance, which I will discuss later on, and increase the reproducibility and productivity of designs. And I would like to show you this quick video that explains how this brief first search algorithm works, and I will narrate the video. I will try my best. And so the round things that we see in the round balls are the nodes, and the lines connecting them are called edges. So we start with a root node A, and we insert it into a queue. The queue is a FIFO. And when we read one element from the queue, we delete it, and we continue to explore the neighbors of that node and insert those into the FIFO again, the queue. And when we reach to an end, to the unvisited nodes, we update the level counter, which we can see in the level 1, it's the 2 nodes. And for each level, we use different colors to represent their difference between the levels. And as you can see, we are done with level 1, and the neighbors of C is also going to be explored later on in the level 2. But now we increase the level counter since we don't have any unvisited node left for the level 2. And brief first search algorithm searches for these nodes again until we finish the queue. Okay, and then the queue is all emptied, and the process is now finished. So why do we need a BFS algorithm? So it's essentially, it helps us to solve some real world problems, such as in GPS navigation systems. So if you want to get from point A to point B in a shortest distance, you need to use the brief first search algorithm. And for the social media, as I described earlier on, you need to find the connections between people, like the mutual friends for the Facebook and the other platforms too. and for the P2P networks too. So the main performance bottlenecks are, so the BFS algorithm depends on irregular memory accesses rather than the computation intensity. So for the computation part, we only calculate the addresses that we are going to next to visit and to gather the data. So it's not computation intensive workload. And we have huge data set sizes. I'm talking about trillions of edges here. And the key part is next to visit node is decided during the execution time. So it's hard to optimize your code according to one data set because there's not one rule that applies for every data sets that we have, since the next to visit node is decided during the execution time. And overall for BFS, we can easily say that computing is cheap, but moving data is expensive since these irregular memory accesses. And this is a conceptual overview of our architectures like memory BFS and streaming BFS. So the conceptual explanation still holds, but this is the way that we try to implement this. So as you can see on the left, there's a small graph example here again, and we picked up the node F as a root node, and we loaded it into the next to visit pipe. And at the same time, so we show our adjacency matrix here as a dense format to make it easy to visualize, but we use it in a sparse way. And we split this graph into two for this example with two compute units. So the compute unit 0 will get the gray shaded area, and compute unit 1 is going to get the unshaded area. In the next event, we check for the, so we read from the pipe and we get the neighbors of F. So for this, we check for the cells that have the in F column value of 1, and we check them in the visited vector if they are visited before or not. Since for this example, they are not visited, we update the updating mask vector to have these values as a 1. And in the next event, for the third column, when we read these updating mask vector values, we update the level vector. So each level, so B and D is going to get the level 1. They will be 1, and F is 0. That's the root node, and the unvisited ones are at -1. And we update the visited vector to highlight these again, and we load them into the next to visit pipe for the next iteration. And this process continues until there's no node to visit. And during this time, we reset everything before restarting again for the other processes. So our approach, our first approach is the memory BFS. So it uses the off-chip DDR memory to share the data between kernels with USM programming model, and leverages the automatic cache memory to mitigate these random memory accesses, which I mentioned earlier on. And it uses the coarse-grained parallelism alongside with Qualys write-back support. And it's designed following the Intel onAPI guidance. And we have 4 kernels for the memory BFS. The first one is the parallel explorer kernel, which performs the dot product operation. And the parallel level gen updates the level vector. These both works on shared buffers, which I will mention in the further slides. And the pipe gen works in parallel with level generators, and it generates the list of newly visited nodes. And the mask remove prepares the binary vectors that we mentioned earlier on for the next stage. So the load balancing is important since, as you can see, those 4 Explorer kernels are running in parallel. And we don't want one of them to finish earlier on and to wait the others to finish their process. And that's why, so we try to optimize our data sets, but since we can't get out of, so since this is a behavior of the data sets, in order to eliminate this, we put some wait statements to make sure that they are all synchronized before moving to the level generator and pipe generator and for the mask move. So in order to achieve this load balancing, we use a Python helper script, which I will talk in a short time. But I want to introduce you the overview of our organization for this system. So the architecture that we use. So we have 3 main elements. So the main memory, which stores the CSR format to the graphs. And we have the CPU, which it takes care of all initializations and it's a bridge between the main memory and FPGA. And FPGA is where all the magic happens. So we do all the calculations related with and do all the data requests. And in parallel, we run the Python helper script, which converts the text, the graph data sets that you have into the binary format, which allows us to have a reduced storage space for like around 10x for giant graphs. And it partitions the graph according to the user needs. And these partitions occur either edge split or not split. And so which one is better? That's a tricky question because it varies. As you can see from the table, if we use the edge split, and that means the number of edges are going to be more or less same when we partition them. But as you can see, there's a highly difference between the number of nodes that we have. And this grows when we move to the bottom part of the graph, that data set. That shows a giant, that's a bigger data set compared to the top one. And the difference increases. So so we need to come to conclusion that to decide for this decision, we need to decide about whether node processing or edge processing is the key factor in our execution time. And for our data and design, it supposed to be better. And in the overview picture that I showed you earlier on, which we have a small snippet here, that example is actually edge split, since it shows equal number of non-zeros in both shaded and unshaded area, which is 9. And moving on, so we use automatic caching in memory BFS in the Explorer kernel. So for this automatic cache, we use 1 megabyte of size. And for this size, we experimented other different sizes too, but we found that the 1 megabyte is the sweet spot for this case. So we used automatic cache to cache the edges and also the visited nodes data while we are loading them, since in our execution, we need to revisit them again at some point. And moving on, we use the coarse-grained parallelism in memory BFS. So in our big picture, we can see that we have 2 level generator. One is level generator high and the other one is low, which means that while accessing them, like the USM dist and USM visit vectors, we employ half of this. So they are n-sized, which means number of nodes that we have. And we employ half of these to the partition of the lower half of the USM dist, and the level generator high will get the higher partition of the USM dist, which allows us to have coarse-grained parallelism while we are accessing the USM dist and USM visited, which increase the performance. And moving on, we use the coalesce write back in memory BFS. So essentially, in summary, what we did was, instead of writing to the main memory in every iteration, we packed all those values that we are going to write in a temporary storage, and then we write them in chunks, which allowed us to have an initialization interval to be 1, and this increased the performance drastically. And the key concepts here are the buffering and the data streaming. So the buffering tells us the temporary, so this temporary storage of data allows us to have reduce the I/O communications, and so we minimize them. And for the data streaming, we process the data and move it out of in chunks, which enable us to have efficient use of resources. So these were the key things that we used in memory BFS, but we had lots of discussions about what we could do better and what we could achieve better performance. How can we achieve better performance? And here we can see that this memory BFS approach that we had has some key limitations, which were the scalability issues. So we were only limited to 4 compute units. And we had some global memory access bandwidth issues. And this was the main target that we tried to improve in our next version, the streaming BFS. And the performance results we'll discuss later, but they were in the middle of the other state-of-the-art performances. So, okay, now we finished with the memory BFS and we moved to the streaming BFS, which is our new approach for this solution, the new architecture that we designed. It's a complete revamp from the memory BFS. So the new features that we added were the data flow execution model. So we use the pipes to stream data between kernels instead of using the off-chip DDR memory with USM programming model. And the new kernel designs with additions. So we use new kernels instead of the old ones, and we ensure the synchronization with minimal latency. And we compressed the data to bytes, and we did some bit manipulations instead of using the arrays. And we replaced some of as I said, some of off-chip memory accesses with on-chip data movement. And it's a new modular design, so modifying number of compute units, FIFO sizes, and cache sizes are from CMake variables, which makes it easier to modify our specs. So first of all, we started with the data flow execution model in streaming BFS. So instead of having those wait commands in between the kernels, we employed the pipes to achieve better performance, since it allows us to stream data when it's ready to the next kernel. As you can see from here, instead of the wait commands, we had now FIFOs, like these pipes, that we can stream the data between the kernels. And also, we divided this the giant Explorer kernel into 3 different FIFO kernels, namely Explore Read, Filter, and Write. This allowed us to have better data transfer between the kernels, since they are now reduced in size. And for the increased parallelism, instead of using the level 2 level generator kernels, we employed them into the, and what I mean is like the number of compute units times level generator in parallel. So this allowed us to increase the performance too. So the bit manipulations in streaming BFS is, so in traditional BFS implementations, and also in our memory BFS model, we used Boolean array to keep track of visited nodes. So for example, if we assume we have 16 nodes, we created a Boolean array of size 16, and we were trying to access one of each when we tried to write them. But instead of this, we transitioned into a new model. So instead of having a single bit Booleans, we employed a char, which gave us 8 bits per array index, and we had size 2 array now. And for example, if we want to write to the bit number 3, like the node 3 and node 6, we don't need to load the data back from the main memory. We just write them into the temporary variable and store back and modify, and later on, when it's finalized, we write it to the main memory at that time. So this increased the locality and combined with the on-chip memory. And this pipe working mechanism is basically what I described earlier on. And so we have a special class that we hold the data and also the valid flag for our data, and we compress our data into chunks, and we use this streaming data class to pass the chunks, which allowed us to have higher performance with the pipe. So instead of passing 1 node data into the pipe, we were passing 8 node data at the same time from streaming one kernel to other kernel. And our next improvement is that we use sort filter kernel mechanism, which is different from the shift register implementation from the onAPI GitHub repository. So instead of inserting the new value into the right-hand side, right end for the FIFO, we insert the new data into the next empty space. So for example, here, we have a sort FIFO with data inserted into it previously. And first, we do the modular operation for the index 0 elements of these sort FIFOs. And so we rank them from 1 to 8. And each clock cycle, we pass one data at the same like level to the next one, so that it allows us to have some local data accesses here in the filter FIFO. And I mentioned about this on-chip memory cache previously, so it increased the locality, and same with the implementation from onAPI samples repository. And I describe about this packing and passing data from the pipes too. So in summary, the streaming BFS, we talk about these improvements as I mentioned earlier on, but this also has some key limitations. So the sort filter kernel is II2 now, which I described earlier on. And during the routing and timing of the design, larger designs have a frequency hit. And the synthesis and performance comparison shows better insights about these heats with the frequency. So this is the synthesis results for the memory BFS, and this does not have the information about the automatic caches we used. This is how the report is generated. But as you can see, the generated design has low utilization values, and there's a slight decrease between the frequency values from moving from one compute unit to several compute units. And the limitation is so the heat is related with the memory bandwidth issues that we have, that I described earlier on. And for the streaming BFS, we have different cache sizes, and this now includes them since it's a custom caches that we use. And as you can see, for these small cache sizes, routing and timing limit us to have a number of compute units of 6. But when the cache sizes are increasing, the BRAM limits us. And now we are limited to a number of compute units of 2. And the frequencies are now lower compared to the single compute unit versions. And the performance variation against the number of compute units is as follows. So for the memory BFS and streaming BFS, we tried to test different RMAT graphs that we use for testing these graphs, like testing the designs. And as we can see, as the edge factor is the key driving factor, the ones that have a bigger edge factor is achieving better performance. But the characteristics of these performance graphs shows us a different insight about the data that we have. So for example, as you can see from the from the memory BFS, it starts low and increases until the 2 compute unit version, and then the performance gets hit. And on the other hand, for the streaming BFS, the performance starts low, but we expect it to achieve higher performance until 6 compute units, which shows us the streaming BFS removes the bandwidth limitation occurred in memory BFS. And this is our performance evaluation data table. And we divided our table into mainly 2 different categories. So the gray highlighted ones are the high-level languages, and the purple ones are the low-level, the hardware description language works. And as you can see for this, so some works are missing some data since the hardware description language is focused on small graphs. And we have lots of performance variations, which we provided lots of insights about these results in our paper, which I suggest you to read it. And there's one insight that I would like to show is these highlighted ones are the small data sets, small word real data sets, and the other high-level language works didn't want to test them because they're really small and their performances got hit, and we tested them, and it seems like we are better than the hardware description languages for these small word data sets even. And summary for today is, so we achieved 1021 MTES peak performance, and I would say that the pipes are, so we achieve better performance thanks to the pipes, and the compression of the data helps to improve the performance drastically. And thank you for listening to me. And if you're interested in FPGAs, you could apply for an account for the Paderborn Noctua 2 system to experiment them. And thank you.
So very nice work. Thank you. Have you tried anything on GPUs just for this?
Yes. So this is our future plan. Since the deadline was approaching, so we couldn't try with the GPUs, and that's the future plan for the next work.
Okay. Thank you.